So this is question set 3, part 1, asking about the student argument on this pulley. So the information that we have of the pulley is that there are 2 A values and 1 B value. So this inner radius is half of the outer radius. The student said the larger mass is going to create counterclockwise torque, and the smaller mass will create clockwise torque. So this larger mass has a radius value out here, like this, R, crossed with this force that's down like this, so that will indeed create counterclockwise torque. And the student is also right about the red one, which is out at a distance here, and has a downward force. That is going to create a clockwise torque. So the student's doing good so far. Then it says the torque of each will be the weight times the square of the radius. Now we can stop there and we can understand the student is wrong in just saying this because the torque will not relate to the square of the radius. Torque is R cross F, not R squared cross F. So that's an issue. No need for the R squared. Then obviously his contention to follow about doubling the radius and smaller and so on and so forth doesn't exactly work because it deals with squares. So another problem that we see is the torque will be the weight times the square of the radius. The torque won't be the weight. The torque will be the tension related to the weight, and that's pretty different, even though I know it's subtle. Because on the 1.5 M, we have tension up, we'll call it TA, and we have 1.5 mg down. If there's any sort of acceleration, then those two forces cannot be equal to one another. Therefore, what's pulling on the pulley is not 1.5 mg, but is actually TA. And same for this mass M. These two cannot be equal if there's acceleration. One of them is winning. And therefore, mg is not directly pulling on the pulley, but TB is. So that section is wrong. Last, he says the net torque will be clockwise, so the angular acceleration will be clockwise. We can look and imagine if there was no acceleration, if there was no acceleration. So alpha equals 0. Then you could say that the torque from the counterclockwise would be the R value times 1.5 mg R cross F. Well, the torque from the clockwise, which is red, hope I said that right, will be the, I'm going to make this R subscript A. So the torque from the red will be R subscript B times mg. And remembering here that we can, with subscripts, rewrite our radii, you can replace RB with 2RA. So if acceleration equals 0, then the clockwise torque is more. And that's a good way to think about what's going to happen to our system. So let's go ahead and actually solve part B. Part 1 is over. We've addressed the student is right in some regards and wrong in others. The next question asks if we were to remove the red block. So we're taking away the red block like this. We're removing this torque term. What is going to be the acceleration, the linear acceleration of the 1.5 mg? So here's our free body diagram of our hanging mass, and here is our pulley. So it tells us that the pulley can be estimated as a disk, 1/2 of mass m, related to that m, and a radius b. So R. Let's go ahead and we'll sum torques here and we'll sum forces here, and then we can combine the two. So for here, I'm going to be careful to call this tension, TA, at a distance R. A equals our I value, 1/2 m, RB squared, and alpha. Now over here, I want to think about which one's winning. In this case, there's only one mass, and so we're going to see our system move counterclockwise due to that mass. So our 1.5 mg will be winning. So down here, we're going to have 1.5 mg minus TA equals m, 1.5 m. A. So what I did there was I summed the forces, and I set them equals to ma. Now this at first seems no good because it feels like you have too many unknowns. You don't know tension, and you also don't know acceleration, and you also don't know alpha. But if you remember, you can take this step where you can rewrite alpha. So alpha can be rewritten as A over R. And in that case, we can simplify everything down. You want to think about what is the radius value, RA or RB, that relates to linear and angular accelerations. So for us, the radius value is going to be R subscript A, because it's the smaller radii that actually physically attaches the linear motion to the angular motion. So instead of alpha here, let's put A over radius A. Okay, so we'll simplify this out. So we have, I'd like to also write RB. Remember our relationship in the beginning of the problem? RB is 2RA. So let's put that in as 2RA. So we'll have 2RA. So now we have an RA squared and a 2 squared. So our RAs are going to cancel here and again here. So we're going to be left with tension A equals half our mass times our linear acceleration A. Let's go ahead and let's take this simplified expression and plug it in right here. So then over here we're going to have 1.5 mg minus, instead of t, we're going to write half ma equals 1.5 ma. Let's cancel the m's. 1.5 g. Let's add the half a to the other side. 1.5 a plus half a. 1.5 plus half, that's 2a. So now we can solve and we can find that acceleration is going to be 1.5 g over 2. Now it makes sense here that our acceleration is less than the value of gravity, right? That's good. We can plug back into wherever we want to find tension. So we can put this in here and we can say tension in chord A is 1/2 mass times 1.5 g over 2. If we want, we can find alpha, because alpha is A over RA. So that would just be 1.5 g over 2 RA. And that's it.